This example is taken from a kinase project in which a large screening campaign has resulted in a hit list. The project team wished to evaluate the list to identify the chemotypes within and focus their resources on a small number of series that have demonstrable SAR at the target and are most likely to yield high-quality leads with appropriate physicochemical and ADME properties. In the following steps, we will utilize the features of CardView to quickly and easily accomplish this task. From the File Open menu, open the data file cdk2 triage _pic50.txt. This is a text file such as can be saved from Excel. The file import dialog shows that the text file contains 4 columns. The first contains compound identifiers, the second experimental data for the potency, the third has compound structures, and the last is a chemical series tag. Click the Next button and then Finish to complete the import, and the dataset will be displayed in StarDrop. We have no further measured data at this stage of the project, so we're going to generate some predictions of ADME and physicochemical properties. Click on the Models tab. To run all of the StarDrop models, click the tick box next to the word StarDrop. Click the arrow button on the Models tab, and a progress bar will be displayed while the predictions are calculated. When this process is complete, you will see that a new column has been added to the dataset for each property calculated. We will now change from the table view of the data into card view. Click the Card View button on the toolbar. Now click the Design button in Card View and select Custom from the menu that appears to open the Card View Design Preferences dialog. Here we can design the way we'd like our cards to look, but for this example we're going to load a template that we've saved earlier. Click the Load button and then select the file cdk2 triagedesign.xml and then click OK. The cards are now displayed using the selected design, and the first card is positioned in the center of the screen. You can move the view of the cards by holding the left mouse button down and dragging the view. You can also zoom in and out by using the middle mouse wheel or holding the Control key and pressing either the minus or the equals key. You can also move individual cards simply by clicking on them and dragging them. To quickly see which compounds have an acceptable activity and solubility profile, we can group the compounds into stacks. From the Organize menu at the top of Card View, select Stack, then Recursive Partitioning. Choose cdk2 pic50 as the property to bin the cards by, and then click the Edit button, increase the number of bins to 3 and change the boundary values to 5 and 7.5. Now click the Add button to add an additional property of solubility, and then split this into 3 bins as well, with -0.5 and 1.5 as the boundary values. Once you've done this, click OK to perform the stacking. The top right-hand stack has interesting compounds, 38 of them, because they are potent and predicted to be soluble. Double-click on the stack or right-click and choose Inspect to look at the cards within that stack. A number of different chemical scaffolds are represented in this stack of desirable compounds, which might increase the project's chance of success. But we would like to know how these series are distributed across the whole dataset. For this we need to define the chemotypes in the set, which we can do by clustering the dataset based upon the common substructures. From the Analyze menu at the top of Card View, select Clustering. Choose the Common Substructure option, enter a similarity value of 0.4, and then click Cluster. Each of the stacks represents a set of compounds which share a common substructure, which is displayed on top of the stack. The stacks are laid out based upon the relative similarities between those common substructures. You can see that there is a group of 3 stacks on the right that all have various decorations of an aminopurine core. These 3 stacks could be thought of as a single aminopurine series and can easily be combined manually into one stack. Choose the Lasso tool from the Card View toolbar and draw a ring around the 3 stacks. The selected stacks can now be combined by right-clicking on the selection and choosing Stack Selection from the menu. The new common substructure of a monoaminopurine is now displayed. We can repeat the grouping process for a set of pyrimidinol quinolinones in the main group of stacks. Here, with only 2 stacks, we can use the Hand tool to simply drag one stack on top of the other to group them together. We can easily rename stacks, simply clicking on the name below them and editing it. We can easily combine stacks in this way and rename them as appropriate, But to save time in this example, this process has already been done for you in this dataset. The stack names for the chemotypes are entered under a column called Series. To view the dataset with these defined series, click the Organize menu at the top of Card View and choose Stack by Property. In the Stack by Properties dialog that appears, choose the Series column from the drop-down list. This stacks the cards into 10 stacks, which have the common substructure detected within the stack. As the series definitions here are human-derived, there are some stacks that do not have a large enough common substructure for display. The stacks can be laid out in a more compact grid by clicking the Layout menu at the top of Card View and choosing Grid. More relevant information about the property distributions for the cards in the stacks and a representative compound from the stack can be seen by applying the CDK2 Triage design template again. You can do this by clicking the Design menu at the top of Card View and choosing User Designs CDK2 Triage Design from the menu. The histograms on the stack covers show the distribution of key properties of the compounds within each stack. Potency as a histogram, HERG-PIC50 as a box plot, and log S as a compact histogram. These displays can help to answer the question of which series has a good range of potencies as well as acceptable solubility and/or HERG-PIC50. We can see from the list of stacks that the amino nonpurines, 2-aminopyrimidine 4-arrow ring, and the 2 pyrazines series all have compounds with good activity. However, the solubility distribution looks more promising for the amino nonpurines, whilst the aminopyrazines appear to have the better HERG profile. Next, we shall examine one of these clusters to see what SAR points can be learned from a particular series. Select the 2-aminopyrimidine 4-arrow ring stack, and then from the Dataset menu, choose Create from Selection to put these compounds into their own dataset. Give this dataset a name, click OK, and then we'll switch back into Card View to look at these compounds in more detail. You can see how properties are distributed across this chemotype by clicking the Organize menu at the top of Card View and choosing By Property. Set CDK2 PIC50 as the X direction and log S as the Y direction, and then click OK. Hovering the mouse over a card will enable you to see it in more detail, but these cards can also be coloured by properties using the Colour button. In the Colour by dialog, select HERG-PIC50 and change the interpolation scale to go from 4.6 to 6. Note that the top right-hand corner of the display, which corresponds to good PIC50 in solubility, has very few red cards which indicate inactivity at HERG. This means that there is a conflict in this series between having soluble potent compounds and low HERG activity. This is something which could be addressed using StarDrop's probabilistic scoring approach to identify alternative structures within the series which have a better balance of properties. But scoring is something which is covered in some of the other examples that you can find in the tutorial section of the Optibrium community. However, the more detailed SAR in this chemotype can be investigated further by finding the matched pairs within the set. Click the Analyze menu at the top of Card View and choose Find Matched Pairs. Colour the links by differences in the potency, and click OK to run the matched pair analysis. The results will be shown in Card View as a network in which each matched pair is shown as a link between the corresponding cards. A table will also be created showing a summary of the matched pair transformations, the individual matched pairs, and a histogram enabling you to see the distribution of changes in a property for the matched pairs. As the cards are still coloured by predicted HERG, we can see that the non-paired molecules in the grid at the bottom of the display have a lot of the lowest HERG activity value, as shown by the red cards. Some of these compounds still have activity at CDK2, so they have the potential to be exploited as new leads in this chemotype. The coloured cards in the main networks show that variations in HERG activity can be achieved. Also, similarly coloured cards with deep red links connecting them indicate that HERG activity and potency SAR can be separated. This provides a further indication of the potential developability of this chemotype. Sort the transformations table by clicking on the header of the count column and then select the chlorine to hydrogen change, which has 5 occurrences, so that we can focus on those pairs of molecules. The delta CDK2_PIC50 column shows that this change is associated with a major change in activity, an average of 1.8 log units. As you click on the different examples of this transformation in the matched pairs table below, the network display in Card View zooms into that pair of compounds. We can see that it is the unsubstituted phenyl ring derivative which is the best compound, and the various chlorine substitutions are much less active. The matched pairs analysis has highlighted single point changes that occur within the dataset, but we are also interested to see if there are other changes which have a significant impact. For this, we first need to select a specific compound, which in this case will be the unsubstituted phenyl compound. Select this compound and then click the Analyze menu at the top of Card View and select Activity Neighbourhood. In the Activity Neighbourhood dialog, choose to colour the links by CDK2 PIC50, choose 20 as the number of nearest neighbours, and then click OK. To make the structures more prominent, we can change the card design. Click the Design menu at the top of Card View and choose Diagram Only. Click the Colour button to bring up the Colour by dialog again, and colour the cards by the potency, interpolating from 6 to 9. From this analysis, we can see that not all substitutions on that phenyl ring are disfavoured, as those compounds having a parasulfonamide substituent are equally potent. Hovering the mouse over a link will show the pair of compounds at either end of that link side by side. In the Activity Neighbourhood results, the nearest neighbours table can be used to view the effects of these changes across the range of properties in the data table. Click twice on the header of the delta CDK2_PIC50 column to sort the columns such that the positive changes are at the top, and then check the Show Heat Map box. Here we can see that there are changes which keep the activity, the pale or white colours in the delta CDK2_PIC50 column, decrease the log P, the blue colour in the delta log P column, and also increase the solubility, the red colour in the delta log S column, indicating that these features can be optimized independently of each other in this series. Again, this is a positive indicator for the potential successful optimization of this chemotype. Click on the first row in the nearest neighbours table and the display will focus on that pair of molecules. This view can summarize the SAR in the series and can be captured by right-clicking on the view and selecting Copy Image from the menu, enabling you to paste this into a slide or document. Similar analyses can be done for the other chemotypes to produce a full report for an HTS triage. For worked examples showing more of StarDrop's features, take a look at the tutorials section of the Optibrium community.